Alright, welcome to the second video of 3 deviations from multivariable calculus. Today we have an important video because we're discussing one of the most fundamental topics in the whole course. Now, we will be using this for the first unit, the second unit, and the fifth unit. So they're very important. They're very important to describing our world. So we'll be introducing vectors algebraically today, and then we'll go over some properties next time, and then we'll go over some of the vector products, which are also very important in future videos. All right, so we'll start off with just introducing vectors. So what is a vector? So we know what a scalar is. We've been dealing with scalars for all of single variable calculus. A scalar is a one-dimensional object because this scalar only has one point. The scalar can be big, it can be small, but we can describe it only with a magnitude. So a great example of a scalar quantity is the number line. So R is a scalar because, or if any number x is in R, then x is a scalar. And so it's a good way to think about a scalar. Now, a vector is something with a magnitude and a direction. So a vector can be thought of as an arrow because it has a magnitude denoted by the length of this arrow, and a direction noted by its angle from the horizontal or the ratio of its x components and its y components. We can determine what its direction is. Now, a vector needs more than just one number to describe it. So a vector requires however many dimensions are in your space to describe it. So if I have a plane, if I have a 2D plane, then I need two quantities to describe my vector. Now these are often, we call a vector A maybe, and vector A is described by its x component and its y component. We'll go into components later, but then in 3D space we need three. We need its x component, its y component, and its z component to describe a vector. Anyways, that's my little tangent on vectors, no pun intended. All right, now we can actually talk about how we combine vectors. So if I want to add a vector, I take a vector and I add the vector tip to tail. So if I want vector v, if I've got vector v, and I want to add vector u to it, so vector v plus vector u, then that is just, if I put u at the tip, if I put the tail of u at the tip of v, then I get v plus u. So we make a new vector, and this vector is v plus u, okay? And we have a law called the parallelogram law, which says that if I elect to do u before v, if I elect to do u, let's say if I do u here, or if I do u here, then I do v there, then that's going to yield the same sum. So the parallelogram law says that u plus v equals v plus u. Now the same goes for subtracting vectors. If I want to subtract it, instead of adding tip to tail, I will add tail to tip, or I will add tail to tail or tip to tip. And that will give us our subtraction. Okay, so that's the combination of vectors, how we add them, kind of geometrically, really. Now let's cover another important thing, which is multiplication by scalar. So scalar multiplication, because scalar only has a change of magnitude, it will alter the magnitude of the vector. So if I do c times v, so if I have a vector v, this is my vector v, then c times v, if c is a number that's larger than 1, then our vector cv is going to be larger. Then our vector is going to be larger than v, positively. And then if c is smaller than 1, then we're going to get a short vector. And then if c is negative, then we get a negative vector. So that's c times v with c less than 0. Okay, so that's how we do scalar multiplication. It's fairly easy. So now scalar multiplication and addition we understand geometrically. Those are the really two important ones that we need to understand geometrically. Now let's try to understand them algebraically. I was speaking about components earlier. Now components are a way that we can mathematically understand vectors a little bit more easily. So if I have a vector v, I can describe this vector v by its x component, which I will call v sub x, and its y component called v sub y. So this is fairly analogous to how we use an ordered pair to describe a point. We use these components to describe a vector. So the x component tells me how far along the x-axis my vector is, and then the y component tells me how high the vector is off of the axis. And obviously you can use Pythagorean rules to determine how long the vector is, but we'll go into that later. So anyways, in 3 dimensions, I have a vector v, and my vector v is equal to this column vector, or column matrix, v sub x, v sub y, and v sub z. So these are my components. So this tells me how far in the x direction, this tells me how far in the y direction, this tells me how far in the z direction. So given, if I have if I know a point A, and I know a point B, and I know the components of the point A, or I know the ordered pair for the point A and the ordered pair for the point B, then I can describe a vector between A and B. So I just take the difference. So if I have, I'll do this in 2 dimensions to make this easier, but if I have a point A here and a point B here, I want a vector from here to here, then this is going to be delta x is going to be my x component. This here delta y will be my y component, and we can describe that here. So I'd take b sub x minus a sub x, b sub y minus a sub y, and b sub z minus a sub z. That should seem fairly trivial. This is how we describe a vector given 2 points, vector between 2 points. All right, so now let's do an example. Let's find a vector from point A to point B if A is 2, negative 3, 4, and B is negative 2, 1, 1. So what we do is we just subtract the B's from the A's, or we subtract the A's from the B's. So we get A is equal to negative 2 minus 2, 2 minus negative 3, and 1 minus 4. So we get vector A is equal to negative 4, 4, and negative 3. So that describes our components for our vector. All right, so now what I'd like to do is I'd like to discuss in more depth the lengths or magnitudes and the operations that we can do algebraically. So I'm using an n-dimensional case. So this works for 3 dimensions and 2 dimensions. It works for any number of dimensions. But let's say that I have a vector A. This is equal to the column vector a sub 1 all the way to a sub n. So we have all of those n components. So then if I want to find the magnitude of A, I can just use the Pythagorean theorem. So I take a sub 1 squared plus all the way up to a sub n squared. So it's just the Pythagorean theorem. Likewise, if I want to add 2 vectors together and I know their components, well, I just add by component. So if I want A plus B, I take a sub 1 plus b sub 1 all the way to a sub n plus b sub n. Then likewise, for scalar multiplication, I just apply that scalar to every component separately. So that's what's really important about vectors. You can deal with things separately for now, and then it should all be smooth sailing. All right, so that's our video on vectors. So this is a fundamental approach to how we deal with vectors, fairly abstract approach. But in the next video, we're going to talk about vector properties and basis vectors. So that's a very important topic that we will cover later. Thanks for watching, and we'll see you next time. Bye.